Alright guys, welcome to Math 0314. We are in section 5.5, rational expressions and rational functions. So, first things first, what is a rational function? What is a rational expression? So, rational functions are, well, let's back it up a little bit. What is a rational number? So we said a rational number is of the form a over b, where a and b are integers and b cannot equal to 0, right? So a rational expression is essentially the same thing. Now, one thing I do want to note here as I'm writing this and thinking about is if you have something like 1 over 2, 1 over 3, realize that this is actually the same thing as 3 over 2, right? If I multiply both top and bottom by 6, these will divide out and give me 2, these will divide out and these will give me 3, right? And it's okay to multiply by 6 over 6 because 6 divided by 6 is 1, so I'm not changing the expression. So even if you have fractions here, when you reduce the fractions, you actually end up getting 3 over 2. Another way of showing this is to say this is 1/2 divided by 1/3, which is the same thing as saying 1/2 times 3 over 1, which gives me 3 over 2. Okay, so with that being said, what we're going to start off doing is we're going to take these rational expressions or rational functions and going to state what the domain is. Now, notice here when we wrote this out in the definition, we said b cannot be equal to 0. It's a little foreshadowing because what that means is that the denominator can't be 0. So what I need to start off doing here is that we just take the denominator. It can't be equal to 0, so we solve and we say x cannot be 3. How did I do that? Obviously, I just added 3 to both sides, and I got x can't be 3. So we can write this in set notation as x such that x does not equal to 3, or in interval notation as negative infinity to 3 union 3 to infinity. So let's be clear here. What we're saying is everything is true except at 3. All right? Except at 3. So all of these values here would be true, all of these values here would be true, but there's a point here at 3 that it cannot be true. And if you don't believe me, you can plug in numbers. Plug in any number but 3 and see if you can create a y value. And you'll quickly see that that is the case. You will always get a y value if you plug in anything but 3. Because at 3, you have 0 in the denominator, and when you divide by 0, it's undefined. So, if you take a look at number 2, it's more of the same. We're just going to say x plus 6 can't be equal to 0. So by the same math from the previous problem, we get x cannot be negative 6. Okay, so in interval notation, this would just be negative infinity to negative 6 union negative 6 to infinity. And here we would write it formally as x such that x does not equal to negative 6. Now, what I always hear students talk about is this x plus 2, and they say, well, Mr. Anderson, what about the x plus 2? Well, x plus 2 is irrelevant in this problem. The only concern we have is that the denominator can't be 0. So don't worry about x plus 2. Moving right along, what happens in number 3? Well, we still want to say the denominator can't be equal to 0, but we have a problem here. And the problem with the denominator is we have a trinomial. But we know how to factor a trinomial. So we're going to start with 2x and x, and I'm going to go 1 and 5. So if you're concerned with where did I get 2x and x from, it's the fact that what times what gives me 2x squared? 2x and x. If you're concerned with where I got 1 and 5 from, it's what times what gives me 5? 1 and 5. Now the tail end of this is that we want to see if we multiply these two, we get 10x. 10x, and on the bottom part, if we multiply them together, we get 1x. And the goal is, can I add 10x and 1x and get to 11? Well, if we make them both negative, we will get not only 11, but negative 11. So that's exactly what we need to see. They're both negative. So then we can say 2x minus 1 cannot be 0, and x minus 5 cannot be equal to 0. And if you're having any doubts where this is coming from, then that just means you need to go back to 4.8 and review 4.8. That's all I'm really working through. All right, so from here, we're going to add 1 to both sides. We're going to get 2x cannot be 1, and if we divide through by 2, x cannot be 1/2. Over here, it's simply adding 5, and x cannot be 5. So, what we have here in set notation is x such that x cannot be 1/2 or 5. And in interval notation, this is the more interesting one. We have negative infinity to 1/2 union 1/2 to 5 union 5 to infinity. And hopefully that makes sense, because if we don't exist at 1/2 and we don't exist at 5, the first part is represented here. The second part is represented here. And the third part is represented here. Right? And this would be an interval notation. So, hopefully that's okay. Moving right along. This is an interesting case. If we take the denominator, again, we only care about the denominator, and say it does not equal to 0, when we solve this, we get x squared cannot equal to negative 4. But something should be eye-opening about this, which is that anytime you square a number, you should be getting a positive result. Some people would take the next step, which is to take the square root, and then you would realize you cannot take the square root of a negative 4, right? Or at least we haven't talked about that yet in this class. So when that's the case, the only thing left to say is that there is no restriction here. So the answer is x such that x is an element of the reals. This would be in set notation. Or in interval notation, it would simply be negative infinity to infinity. Another way of thinking about this is, what is the smallest thing that x squared can be equal to? What's the smallest number x squared can be? And that number is 0. And if you think about it, now some of you might be thinking, well, Mr. Anderson, what if I make the number negative? Well, if you make the number negative, anytime you square a negative number, you're going to get a positive value. X squared is either a 0 or a positive number. This is essentially all the values that x squared could be equal to. So if the smallest that x squared can be is 0, then the smallest the denominator could ever be, think about it, has to be 4, because it'd be 0 plus 4, which is 4. The denominator is 4 or more. If the denominator is 4 or more, you can always divide a number by 4. That's always legit. Hence, everything will work. So here, you don't get a restriction. Okay? Alright. Well, actually, let me make one more comment here. Keep in mind that this is only true if you have x squared plus a value. If you had x squared minus a value, then I could apply the difference of squares and rewrite this as x plus 2, x minus 2, set each equal to 0 and solve. Or you could literally just take x squared minus 4, say it doesn't equal to 0, and x squared would equal to now positive 4, and when you take the square root, you get plus or minus 1. I'm sorry, 2. My mind was somewhere else. 2, which is what would happen here if we set each of these equal to 0. So two different ways of approaching, but we would get the same answer either way. So keep in mind, just because you see an x squared, you cannot make the assumption that it's always going to be all real numbers. It's only going to be the case if this was a positive. Okay. Now, let's go on to number 5. So this is the real bulk of what we want to be able to deal with. And in this situation, we're going to be simplifying. This is probably something that you will see on the final, so make sure you do understand what's going on here. So what we're going to do essentially is what we've been doing. We're going to factor the numerator, we're going to factor the denominator, we're going to factor the top, we're going to factor the bottom. And if we have anything that's alike, we can divide through and get rid of those terms. So we're going to try to essentially make this cleaner to get rid of all the excess. So when we look at the top, the first move that you should always do when you see a trinomial or actually any sort of polynomial, is see if you can factor out a common term with each of these. So all of these are divisible by 2, and all of them have an x. So I'm going to factor out a 2x, and if I do that, I'm going to be left with x squared plus 6x plus 8. And I'm going to do the same thing on the bottom. Now on the bottom, both of these are divisible by 6. So we're going to put a 6, and it's going to factor out to x plus 4. Alright. Now the next move that I want to take is I want to take x squared plus 6x plus 8. I want to take this trinomial and see if I can factor it. And hopefully it's very easy to see that it's going to factor out to 4 and 2, because 4 times 2 is 8, and 4 plus 2 is 6. Remember, when the leading coefficient is 1, you're asking yourself what times what is 8, and when you add or subtract gets you 6. So we're going to rewrite it as such. And the denominator is still x plus 4. Now that I've factored everything out about as far as I can factor, we can see that we can divide through, and the x plus 4's divide out, and I'm left with x times x plus 2 over 3. And that's going to be my answer. Now the last bit that we want to do here is we want to state what our restrictions are. So what are the restrictions? This is true, but this is only true when the denominator isn't equal to 0. We can only divide through if these are numbers. You can't do 0 divided by 0. That gives you something called indeterminate. So this is true as long as x plus 4 does not equal to 0. And so x does not equal to negative 4. So this is the restriction. It becomes this insofar as x doesn't equal to negative 4. Now, if you're looking at this and you're like, Mr. Anderson, I wanted to take it from the beginning and take 6x plus 24 and say that doesn't equal to 0 and solve. Well, if you did it this way, notice you would actually still get the same answer. So the correct response is it doesn't matter whether you take this situation or the original. Okay. Now, to be honest with you, if you're concerned in any capacity, I would always take the original and set the denominator equal to 0, simply because if you made a mistake on the first step, you would be compounding the mistake here, right? But you can also see that if I took 6x plus 24, it's not that difficult to factor out a 6 and then realize that you would have, say, 6 times x plus 4 equals 0, divide through by 6, and then you're left with x plus 4 doesn't equal to 0, so x doesn't equal to negative 4. So, I don't think it's a far-fetched jump straight here on this one because it's so simple, but if you have any concerns, always take the original one and break it down. Okay, so I think I've beaten up number 5. Let's jump to number 6, and, well, it's a little different, so let's just do it together. So on this one, we're still going to more or less do the same thing. We're going to simplify the top and the bottom. The top has a 2, the bottom has a 4, so 8, so we can divide through by 2, and we'll get 4 on the bottom. We have x squared and x to the 4th. We subtract the exponents. Since the exponent is bigger on the bottom, the result will be left on the bottom. And do the same with the top, and 8 minus 3 is 5. So we're left with this. Now, when we look at the restrictions, remember we have to look from the original one. So this means that x can't be 0, and y can't be 0, because if either of those are 0, we're dividing through by 0, and that's a no-go. That's it. Alright, now number 7, I want you guys eventually to be able to do these on your own, but this is a little different, and hopefully when you see t cubed plus 8, because of this 3, this makes you think of the sum of cubes. Now the sum of cubes, if you recall, if I give you x cubed plus y cubed, you take the square root of, or the cubed root of both of these, then you square this number, and the middle is the product of these. Alright, now the one little mistake that I made is also we said this is same, different, positive, or same, opposite, positive. So this should be negative. And that's essentially what the formula is. So if I'm giving you t cubed plus 8, we're going to take the cube root of t cubed, which is t. The cube root of 8 is 2. Notice 2 times 2 is 4, times 2 is 8. Then we're going to square the first one, so squaring t gives me t squared. We'll go to the back and we'll square it. Squaring 2, we'll get 4, right? And the middle is the product of the 2, which is 2t. So we're here. The denominator will factor into t plus 2 times t plus 2. And hopefully that's not difficult to realize because 2 plus 2 is 4 and 2 times 2 is 4. So we'll have t plus 2 and t plus 2. One pair of the t plus 2's will divide out, and we're left with t squared minus 2t plus 4 over t plus 2, and this is the final answer. Okay. Notice that t squared minus 2t plus 4, sometimes, it's not very often, but sometimes you can factor this out. So keep in mind that if you have some sort of value at the top, you may be able to factor it to get rid of the denominator. So in this case, that's not the case. However, since we're talking about the denominator, hopefully you'll also realize that the restriction would be that t plus 2 cannot equal to 0 and t does not equal to negative 2. And notice that comes from not from the fact that here we're left with t plus 2, but from the fact that the denominator becomes t plus 2 and t plus 2. So, because both of these. So if this was a different value, let's say this was like t plus 3, then I would have to also include it cannot be negative 3. So it would be both. It can't be negative 2 and it can't be negative 3. So be careful. One of the big mistakes is that students take the final result, and it's not really from the final, it's from the initial. It's from the initial. Okay. Let's move on to number 8. And this is also a very, very, very important rule. Now, when you see this, you want to clean it up, but one thing you cannot do is we know we can't just simply cancel out the x's. This would be like saying 5 minus 1 over 1 minus 5. I can just cancel these out. And we know that we can't do that. Okay. So, what can we do, though, then? Well, one of the slickest moves in math is you can always factor out of both of these. You can factor out a negative 1. So if I put a negative 1 on the outside, that's going to leave me with negative 1 plus x. And if you don't believe me, distribute the negative 1 back in. And you'll see you'll get negative 1 times negative 1 is 1, and negative 1 times x is negative x. Okay. Notice that x plus negative 1 is actually nothing more than x minus 1 if you rearrange. So if you flip the positions of these two, you'll get x minus 1, and we have a negative 1 on the outside. And now you see why we did that, because these will divide out, and we'll be left with just negative 1 on the bottom, which is, now technically there's a 1 here, right? So 1 over negative 1 is just negative 1. So another way of saying this is that if you have two values, it doesn't actually matter what the values are. If you have two values that match, but the order is switched and there is a minus sign between them, this will always just become negative 1. So if you see something like x minus 2 over 2 minus x, you can just say it's negative 1. Because you will always be able to do this effect where you factor out a negative 1 and you can rewrite it as such. So, number 9 is actually more of the same. Now, what I hope you see from section 4.8 is that you remember the difference of squares. So what is the difference of squares saying? Well, the difference of squares says, hey, if I can take the square root of both of these, let's do that. This becomes 5 minus x and 5 plus x. Remember, the difference of squares says you take the square root, you take the square root of both of them, and then you write down as plus or minus and plus. The order doesn't really matter. Now, notice what we have here. Well, these two are the same except the positions are switched. Well, that's what we just finished talking about. When the positions are switched, we can just say this is -1. So all of this cancels out to be -1. So we're left with -1 over 5 plus x. Again, the restrictions would be for both of these. So the restrictions would be that x cannot be 5 and x cannot be -5. Right? Because if I plug 5 here, I'll get 0. And if I plug -5, I'll get 0. And I didn't talk about it here, but the same thing is true on this one, right? X can't be -1. Because if x is -1, I'm sorry, x can't be 1. Because if x is 1, 1 minus 1 would give me 0. Okay? And make sure, yeah, I stated that here. Okay. So that is it for this section. One last bit about this that I want you guys to realize is that notice that these problems are cooked up. So if you ever are struggling, look at either if you're asked to factor the top, then look at the denominator. If you're asked to factor the denominator, look at the numerator. And ask yourself, how can I get x minus 5 to show up in the denominator here, right? That's probably part of the key to solving the problem, right? And so we see the same thing in 8. And in 7, once we factor them, we see we have a t plus 2. So there's probably a t plus 2 in the denominator, right? And number 6, well, 6 is not really the case. And number 5, if you weren't sure what to do with the top, you get an x plus 4 in the denominator, right? That should be easy enough on this one. So that means what? The numerator will probably have x plus 4 in it, right? This is, well, I guess that's the rest of this was something different. But that's something to look out for if you're struggling with factoring something. If one side is either whether the top or the bottom is easier to factor out, once you factor that out, you probably will have that in some capacity on the other side. So it's a lot. Hopefully, though, this wasn't too bad. At this point, if you are struggling with things like factoring, that means you need to jump back to and practice some of the homework on Chapter 4. At this point, you should be comfortable with factoring, and what you're paying attention to is more of the canceling out aspect than with the factoring aspect. In any case, keep on working, guys. We're getting through it. See you in the next video.